Hello, Professor. You can start now.
Yeah. Okay. So you should. You already started recording, right? I see. Okay.
Yeah.
So good afternoon to everyone. Let's start the second lecture. Let me start it by recalling the prerequisites for this lecture course. In my lectures, I assume some familiarity with basic algebraic geometry and basic theory of algebraic groups and their representations. So let me write that prerequisites include basic knowledge of algebraic geometry, and also of algebraic groups and their representations. I will try to recall more advanced things in these topics during my lectures, but some basic notions will be used without any reference. So maybe you should keep in mind some of your favorite references in algebraic geometry and algebraic groups to look for things which are not explained in detail. I don't know what are most common references for these topics in these topics for Chinese students, but let me just list some which I know. So for algebraic geometry, you may take, for instance, a book of Shafarevich. Basic algebraic geometry. Or you may take a more advanced book by Hartshorn. But actually, we do not need the whole content of this book, the language of schemes. We shall not use it. So chapter 1 will be enough for the most part, at least for the most part of my course. As for algebraic groups, some of standard reference textbooks are by James Humphrey. The title is Linear Algebraic Groups. Another one is by Tony Springer with the same title. But instead, you may use any one of your favorite textbooks. So actually, the things which I use, which I will use, are most basic, and they are explained everywhere. So, however, to let my story go on smoothly, say, let me begin with a short digest of some basic notions in algebraic geometry and in the theory of algebraic groups or their representations. Of course, I'm not going to teach you algebraic geometry or algebraic group theory. This is rather to recall some basic notions and facts which you should understand in the course of my lectures, and to fix notation and conventions which I use. So, digest. I'm sorry if it will be maybe boring for some of you who know all these things quite well, but anyway, we have to agree about notations and notation and conventions. So we need to spend some time to elaborate on it for some time, for some part of this lecture. So let's start with algebraic geometry. We shall work over some ground field. Which I shall denote by K. It is assumed to be algebraically closed. And of characteristic 0. Positive characteristic will maybe appear at the end of my course if I'll have time for discussing things in positive characteristic. But for the most part of my course, the characteristic will be 0. And actually, you will not lose much. So without essential loss of generality, you may assume for the most part of my course that K is just the field of complex numbers. Okay. So what is my basic notation? I will denote by A to the N this thick A, the affine space of dimension N over my base field. And by thick P to the N, I shall denote the projective space of the same dimension. Let me start by recalling affine varieties. What is an affine variety? At least what is my convention, what I assume to be an affine variety. Affine variety, affine algebraic variety is just a subset in some affine space given by polynomial equations. Say F1, etc. Fm should be equal to 0, where these Fi's are just polynomials in affine coordinates. Okay. This is a set, but this set is equipped with a topology known as Zariski topology. In which the closed subsets are just by definition all algebraic subvarieties in X. Well, affine may be subvarieties. So far, I use the adjective affine. All affine subvarieties. So this means that, again, some other sets given by polynomial equations, but contained in X. It is not hard to see that it is indeed the collection of closed sets for some topology, which is known as Zariski topology. In case your ground field is complex numbers, you have yet another topology on any affine variety, namely the classical topology, which is Hausdorff. Classical Hausdorff topology. Which is induced from the ambient affine space. Which is just C to the n. It is equipped with a natural topology, which all of you understand. This Hausdorff topology is thinner than Zariski topology. There are more closed sets, and of course more open sets in Hausdorff topology than in Zariski topology. Each Zariski closed subset is also closed in Hausdorff topology, but not conversely, and the same for open sets. But topological terms which I use, which I shall use, usually will refer to the Zariski topology. This is our convention. Unless otherwise stated explicitly. If I want to use Hausdorff topology, then I shall state this explicitly. An affine variety is equipped not only with the topology, but also with some nice collection of functions called regular functions. So regular functions are defined on open subsets, on Zariski open subsets in X. What is a regular function? This is a function f on this open subset with values in the ground field, such that it is expressed locally as a ratio of two polynomials. Let me emphasize that I do not require a global expression of f on the whole U as a ratio of two polynomials, this expression is only local. Okay? Now, the collection or the collection of all regular functions forms what is called the structure sheaf. Excuse me, yes? Any question?
The open set last page is Zariski open set or normal
Zariski. When I speak, when I use some topological term without any other reference, without any other adjective, this means that I refer to Zariski topology. Okay?
I see.
Okay, good. So, so all regular functions form the structure sheaf. Structure sheaf of X. I will denote the structure sheaf in the standard way as fancy O sub X. So what is the structure sheaf? It is just the collection of regular functions associated with each Zariski open subset. So OX of U is by definition the set of all regular functions on U, which is of course not just a set, but it is a ring and even a K algebra. The sum and product of two regular functions is regular again, as is visible immediately from the definition. This is what I wanted to say about affine varieties. And now, if I want, let's turn to general case, to the general case. So what is a general algebraic variety in my convention? General algebraic variety. By definition, it is a topological space, which I again denote by X, topological space, X, with a sheaf of functions on X, on open subsets of X, with a sheaf of functions again denoted by this letter O. What does it mean? This means that to each open subset of X, in the topology of X, I associate some collection of functions on O. So that so I don't want to write down all axioms for the sheaf. For instance, if one open subset is contained in another one, then the restriction of a function on one set from this class is belongs to the same class on the other set, on the smaller set, and so on. So we have a collection of functions associated with each open subset of X. And another condition is that this X and the sheaf O is such that there exists a finite open cover of X. A finite open cover, say U1, etc., US. So these UIs are open. And if you consider each of these UIs together with the sheaf O restricted onto this open subset, this means that you consider functions only defined on smaller open subsets contained in U sub I. then this space with this sheaf of functions is isomorphic to some affine variety with its structure sheaf. So essentially, this definition is the same as the definition of an abstract differentiable manifold in differential geometry. You just define this concept locally. Locally, it is an affine variety, but in general, affine open subvarieties are glued together in one big thing. For example, of course, I hope you hear this not for the first time, but if you hear this for the first time, you want to have some example. One of most natural examples of this picture is the projective space.
Hey, Professor.
Yes.
I learned that the variety requires no singularity to use.
So far, I do not consider smoothness. I do not pose any condition on singularity or smoothness. Any variety suits for this definition. So it may be singular. It may be singular. There may be singular points. So far, I do not discuss these things about smoothness and singularity, okay? Let me come back to my example. So you may consider the projective space. And the projective space, as you know, it is covered by affine open charts. There are n+1 of them. Each of them is an affine space of dimension n. In particular, it is an affine variety, the trivial example of an affine variety. And the structure sheaves on these open charts match so that we get a sheaf on the whole of Pn. And this is an example, excuse me, not infinity, but just n. We get an example of a non-affine algebraic variety. And projective varieties are just closed subvarieties in this Pn. Projective varieties are by definition closed subsets in Pn with induced topology and induced structure sheaf. Closed subsets in P to the n. Yet another piece of terminology. So an algebraic variety X is called quasi-affine. Quasi-affine. If it is an open subset of some affine variety, if X is open in some affine variety. And quasi-projective means the same for projective varieties. Quasi-projective, X is quasi-projective. If it is open in some projective variety. Okay. By the way, since I try to give exercises, of course, this digest is not the subject of my lectures, actually, of my course. But anyway, let me give a small exercise. Probably you know how to do it, but let's anyway give it. Exercise, let me put it in red color. Exercise. An example of a quasi-affine variety which is not affine is given by the affine space with one point removed. It is quasi-affine because it is open in AN. Quasi-affine, but not affine. Prove it. Okay. So I shall use the notation. The following notation. So if I have an algebraic variety X, a general algebraic variety X, then the set of global regular functions on X is denoted, of course, in this way. But I also use an alternative notation. If X is affine, or maybe more generally quasi-affine, the algebra of global regular functions will be also denoted in this way: K of X in brackets, in square brackets. This notation will be used mainly for affine or quasi-affine varieties. You may use it in general, but it is not so common. Used for affine or quasi-affine varieties. Why so? Because one can prove that if X is affine, then global regular functions on X are just polynomials in the coordinates of the ambient affine space. It is one of the basic facts in algebraic geometry. So this is the reason for me to use this notation. Okay? Let me go further. So let me say that my algebraic variety X, let me recall this name, this term. Let me say that X is irreducible. If it cannot be decomposed in a union of two proper open subsets. If it cannot be decomposed in a union of two proper open subsets. So the Zi's are properly contained in X and closed. If such a decomposition doesn't exist, then X is said to be irreducible. And in this case, it is easy to see, just by a simple topological consideration, that any two non-empty open subsets in X intersect. They overlap. They have non-empty intersection. And this allows one to define the field of functions on X, which are not globally defined, but which are defined and regular only on open subsets. If you have any finite collection of such functions, then they have a common domain of definition. This allows us to add these functions, to multiply them, and to divide them one over another. So we have a field of rational functions, what is called a field of rational functions on X. rational function field which I shall denote in the standard way as k of x in parentheses. So by definition, it is consisting of all functions which are not everywhere defined. They are defined and regular on some open subsets in X. Maybe more rigorously, we should speak about equivalence classes of such functions. So two functions are equivalent if they coincide on their common domain of definition. But this is a technical thing. I don't want to draw your attention to it. If you know, you should know such kind of things. If you are familiar with basic algebraic geometry, this is for me just to fix the notation. So this is for irreducible varieties, but in general, for an arbitrary variety, it can be decomposed in a unique way into a union of irreducible pieces. So there exists an unique, what is called irreducible decomposition of my X into a finite union of closed subsets x1, xk, which are, as I said, which I closed, irreducible with the induced topology, and not contained in each other. So such a minimal decomposition is unique, not contained in each other. Okay. Finally, let me recall what is the morphism of algebraic varieties. It is a map from one algebraic variety to another one, which is continuous with respect to the topologies on X and on Y, continuous map, and which pulls back regular functions on Y to regular functions on X. More precisely, this map is such that the put it here. Such that the pullback map takes the space of regular functions on some open subsets, on some open subset of Y, to the space of regular functions on its pre-image, on its inverse image. Pi inverse of U, like this. To make it more clear here. Okay. So if the second variety Y is an affine space, then any such morphism is given by a collection of regular functions on X. These functions give the coordinates of the image of a point in X. So these are regular functions on X. This is all I wanted to remind you of algebraic geometry so far. Again, let me say that I do not want to teach you algebraic geometry by this short digest. This is just to remind basic notions and to set up notation. So no more, no less. And now let me turn to, so maybe there are some questions. There are any questions so far? Are there? Not yet? Okay, so this is nice because I hope that all the things you know more or less. Let me now turn to a reminder in algebraic groups. Algebraic groups. So for me, in these lectures, an algebraic group is by definition an abstract group equipped with the structure of an affine algebraic variety. Affine algebraic variety. In such a way, let me denote this group and variety by G. So these two structures, the group structure and the algebraic variety structure, are compatible in the sense, so such that the group operations, the multiplication, and the group inverse are morphisms of algebraic varieties. If this is the case, then we say that G is an algebraic group. Let me emphasize that I consider only affine algebraic groups. So, for instance, abelian varieties are excluded from my consideration. If you know what is it, abelian varieties are not included in this notion.
What variety?
Excuse me?
What variety did you just say?
I'm considering a set. What variety? Abelian. So abelian varieties are excluded. Abelian.
Theoretic variety.
So abelian varieties are not considered in this definition. An abelian variety is a projective variety, which is an algebraic, which is a group such that the group law is a morphism. So if you drop this affinity assumption, then you get a more general definition of an algebraic group, which includes, for instance, projective algebraic groups, known also as abelian varieties. Okay, but I don't want to consider them. So, of course, if again, in the most clear case, if K is the field of complex numbers, then any algebraic group is at the same time a complex Lie group. So you may consider algebraic groups over complex numbers also as Lie groups. And this is instructive sometimes. What is the basic example of an algebraic group? Of course, the basic example, which I will use in many times in different situations, basic example is the group of all non-degenerate n by n matrices, GLN. Why it is an algebraic group? Well, it is embedded as an open subset in the space of all square matrices, n by n matrices, which is just an affine space of dimension n square. This explains that G is a quasi-affine variety, but it is also an affine variety because there exists another closed embedding of GLN into an affine space of dimension bigger by 1, n square plus 1. So this embedding is given by sending a matrix G, a non-degenerate matrix G, to the pair G, comma, the inverse of the determinant of G. So G is non-degenerate, so its determinant is non-zero. And the set of all such pairs is a closed, it is easy to see that it is a Zariski closed subset in this affine space. So you may consider G as an affine variety. So G is an affine variety, affine algebraic variety. And of course, the multiplication of matrices and taking the inverse of a matrix is given by polynomial formulae. So both maps are morphisms of algebraic varieties. So this is a basic example of an algebraic group. And it is not only an example. It is a somewhat general thing. There is a fact, which I leave without proof, referring to the textbooks above, which I mentioned above, that any algebraic group, in the sense of the above definition, any algebraic group G admits a closed embedding, an embedding as a closed subgroup in some GLN. That's why algebraic groups, in the sense of my definition, are also called linear algebraic groups. So for me, algebraic groups are linear algebraic groups. Zariski closed subgroups in some GLN. Let me emphasize this. Okay. Let me also remind you some basic notions, some basic terminology from the theory of algebraic groups. So almost everything what you can do for an abstract group, you can redefine this concept for algebraic groups. For instance, what is a homomorphism of algebraic groups? Homomorphism of algebraic groups, by definition, it is just a group homomorphism of abstract groups which is at the same time a morphism of algebraic varieties. An example of such a homomorphism is a representation of an algebraic group. So in this setting, a representation of an algebraic group is a homomorphism from this algebraic group G to the full linear group of some vector space, which can be identified with the group of matrices of the size, the dimension of this vector space. So it is an algebraic group in the sense of the above example on the previous page. But let me emphasize again that I consider not just an abstract group homomorphism, but a homomorphism of algebraic groups. This means that this representation map should be a morphism of algebraic varieties given by polynomial formulae, if you like. Such kind of representations are sometimes called rational representations. But we shall drop this adjective. Just a representation of an algebraic group. Another important notion in this theory is the notion of an algebraic group action. So what is it? If you are given an algebraic group G and an algebraic variety X, then the action of G on X is the group action in the usual sense. So the group G acts on the set X. Group action such that the action map sending a pair, this is a map from G cross X to X, and it sends a pair G comma X to G dot X, the result of the action on the element G on the point X. So this map should be a morphism of algebraic varieties. Then we have an algebraic group action. And let me finish the first part of my lecture by the following standard theorem. From this theorem, in the previous notation, if you are given an action of an algebraic group G on an algebraic variety X, then for any point x small in X, the orbit through this point is a locally closed subvariety in X. And the stabilizer of the point X, which I denote as G sub X, is a closed subgroup in G. Okay, so I think I shall stop the first half of my lecture here. If there are any questions, then please do not hesitate.
What is a locally closed mean?
Locally closed, let me write it down. Locally closed means open in the closed. Open in closed. This means that you have a closed subset in X, and you take an open subset of this closed subset, relatively open subset. Okay?
So the orbit is not necessarily closed.
Exactly. Exactly. And actually, this is, in a sense, the key point of my lecture course. I will consider some orbits which are open in the whole of X, and X is a kind of compactification of this open orbit. So these homogeneous algebraic varieties on which X acts transitively are not necessarily closed in ambient varieties. This is the point, yes. Any other questions? No questions so far. Then I guess we have a 10 minutes break, right, Kohan?
Yes, Professor. So
we.
Hello.
Yeah. We resume at 20 minutes to 3. Yeah. Not to 3 to because I'm using Moscow time. So 20 minutes to 8 to 6. Yeah. To 7. 20 minutes to 7 in Beijing time. Right?
Hello, Professor.
Yeah. Do you hear me?
So locally closed means that we can find a closed subvariety such that the orbit is opened.
Yes. So let me draw a picture. So you have this ambient X. Inside X you have something closed, say Z, and also you have something open, say U, and when you intersect Z with U, we get this guy, which is locally closed. So it is open in Z with the induced topology. This is what locally closed means. Is it okay? Is it clear?
Yeah, so I mean the picture here, the U is not contained in Z, right? But
no, U is not contained in Z. U is an open subset in X, but when you intersect it with Z, you get an open subset in Z with the relative topology, with the induced topology.
So the orbit may intersect with many close-up variety, and
well, actually, you may consider you may take for Z just the closure of the orbit in X, and then the claim is that in this case the orbit of X is open in this Z. Something like this.
So the orbit must be no, I mean the closure of the orbit must be a subvariety here.
Well, it is a subvariety by definition, because a subvariety, a closed subvariety, is by definition just a closed subset in X.
Oh, I get it.
Any closed subset is equipped with the structure of a subvariety, with the structure of an algebraic variety. The topology is just the induced topology, and the structure sheaf is given by restriction of regular functions from X to Z. Of course, there are some details which should be discussed more thoroughly. But again, as I said, I'm assuming that you know these things more or less, and if not, you should consult these reference books which I quoted at the very beginning. So I just mentioned some basic facts, but mostly without proof, just to recall for you. So there is something to prove here, but let me skip the proof. So I guess that there are yet 5 minutes of our break. So if there are no more questions so far, then maybe I will leave you for a couple of minutes. Just let me. Okay, shall we continue? Let's continue the lecture, the second half of the lecture. So maybe a coming back to this theorem on the screen, maybe I should give an example since there were questions. Let me give an example of this theorem. An example from the previous lecture. So recall that we had a space of quadratic forms, or a space of conics, including degenerate conics, which was interpreted as the projectivization of the space of symmetric 3x3 matrices. So in the first lecture, I used the field of complex numbers, but I can use any field. This is a projective space of dimension 5. And there is a natural action of the group GL3 on this projective space, which is, of course, an algebraic group action by linear substitute of variables in the quadratic forms defining the conics. And you may ask, what are the orbits of this action? Orbits. The orbits are given by the rank of a quadratic form. So the first orbit is given by the condition that the quadratic form is non-degenerate. The rank is equal to 3. Here, Q small, as in my first lecture, Q small denotes either a quadratic form, defining in 3 variables, defining a conic in P2, or its matrix, the symmetric matrix, a symmetric matrix 3x3. So all non-degenerate quadratic forms are equivalent, and all smooth conics are equivalent with respect to this group action. They lie in one and the same orbit. So this is smooth conics. The second orbit corresponds to rank 2. Quadratic forms of rank 2, and they define degenerate conics, which are union of 2 lines. And the third orbit is given by rank 1 condition. So the respective conics are just double lines. So let me denote these orbits as, say, O1, or maybe. Let me enumerate an orbit by its rank: O3, O2, and O1. And it is easily seen that O1 is closed in P5. O2 is not closed. Its closure consists of 2 orbits, O2 itself and O1. And also O3 is not closed. It is open. In P5, open and dense, because P5 is irreducible and each non-empty open subset is automatically dense. And its closure contains all 3 orbits. So if you look at the second orbit, at the orbit O2, you see that it is neither open nor closed. It is locally closed. It is open in its closure. This is the example for the previous theorem. Okay. Now let me turn to less standard and less elementary facts from the theory of algebraic groups, which maybe you know not that good, but let me anyway recall these facts and notions. So I'm using the previous notation. I'm assuming that an algebraic group G acts on an algebraic variety X. So this is an algebraic group action. In this case, I can define the geometric quotient for this action. Geometric quotient. As an algebraic variety Y, denoted also by X over G, the quotient variety. This is an algebraic variety equipped with a morphism from X to this Y, morphism say pi, such that the following properties should hold. First, the fiber over each point of Y is a single G orbit. Secondly, there exists a linear representation of my group G. No, excuse me. This is not this condition which I wanted to put. The second condition is that for any open subset of Y, I would say differently. A subset U is open in Y if and only if its inverse image is open in X. So the first condition says that, in particular, says that the morphism pi, the map pi, is surjective. And the second condition says that Y is equipped with the quotient topology with respect to this morphism. And the third condition is about regular functions. So a function f on an open subset of Y is regular. It belongs to the structure sheaf of Y if and only if its pullback, its lift to X along the map pi is regular with respect to the structure sheaf of X, is a regular function on the inverse image of this open subset U. So regular functions on Y are exactly those functions whose lift to X are regular on X. This is how to reformulate briefly this third condition. And if such a variety Y exists, it is called a geometric. It is called the geometric quotient of X modulo the action of G. But it is important to understand that the geometric quotient doesn't always exist.
May I more or
Yes.
less say that pi upper star f is G invariant function?
Well, you may say like this, but yes, exactly. It is G invariant because it is pulled back from something on Y along the map pi, whose fibers are exactly G orbits. So by construction, this function is constant on each orbit, wherever it is defined. Of course, this implies that it is G invariant. So you may put, if you like, you may put this sign G here, but it is automatic. So G invariant function, yeah. Okay. Okay. So let me again emphasize that the geometric quotient for an algebraic group action doesn't always exist. actually the situation when the situations when this quotient exists are rather rare. So most often it doesn't exist. But anyway, sometimes it exists. And if it exists, then this geometric quotient is unique up to an isomorphism. This stems from these three properties because they define, essentially they define this Y as a set. It is identified with the set of G orbits in X. And the second property identifies the topology in Y. It is what just the quotient topology on the orbit set. And the third property identifies the structureship. So if a geometric quotient exists, then it is unique up to an isomorphism.
Well, I don't think this situation should be called geometric quotient does not exist. It should be called the geometric quotient is not a variety.
You may say like this, but I just started this definition by saying that Y is an algebraic variety and pi is a morphism. But if you define this Y just as the orbit set with the quotient topology and this push forward of the sheaf of invariant functions along the map pi, then in this sense the quotient always exists as a ringed space. As a topological space equipped with a sheaf of rings, a sheaf of algebras. But if you want Y to be an algebraic variety, and if you include this in the definition, then it doesn't always exist. So you are also right, it depends on the viewpoint. So let me say that maybe to avoid disambiguation, let me put here that Y is an algebraic variety. And pi should be a morphism. Okay, but what are situations, in which situations the geometric quotient exists as an algebraic variety, I would say. So let me mention the following theorem. Suppose you are given a closed subgroup in my algebraic group G. Then the following holds. First, there exists a geometric quotient for the right action of H on G. So here, H acts on G by right multiplication. I guess you understand what does it mean. So an element H acts on an element, well, okay, let me write it down. So H acts on G. Let me write it differently. The action of H sends G to G times H inverse. This is the action of G on H for by right multiplication. This is the first statement. The second statement. There exists a linear representation of G on some vector space V, and there is a vector. There exists a vector in this vector space big V such that H is precisely the stabilizer of the line spanned by this vector. The line is just the point in the respective projective space, so I denote it as V in brackets. And this essentially means that the geometric quotient can be identified with the orbit of this point V in brackets in the projective space, the projectivization of V. This second statement is also known as Chevalier's theorem from the theory of algebraic groups. Next, the third statement is somewhat converse to the previous one. Excuse me. Maybe I should add that in particular, this means that the quotient of any algebraic group by its closed subgroup is a quasi-projective variety, because it is an orbit in a projective space, a locally closed subset in a projective space. And the third statement is converse to the previous, to the first one, maybe. Conversely, if you are given any transitive action of G on some algebraic variety X, transitive action, that is, there is only one orbit. And if my H, subgroup H, is the stabilizer of some point X small, then the variety X is isomorphic to the quotient of G modulo H. So to this Y. Let me write. To this Y. So briefly speaking, a transitive algebraic group action is completely defined, is uniquely defined by the stabilizer of any point. Okay? So this is this theorem is more or less standard. It is in any textbook on algebraic groups. Any questions so far?
Can we strengthen the second proposition to irreducible representation?
No, not always. Of course not. No, by no means. I won't give you example, but no. Irreducibility is absolutely irrelevant in this statement. Okay. So, but now let me formulate a statement which is maybe less standard and less known to you. So I keep previous notation. I have a subgroup H, a closed subgroup H in an algebraic group G. And suppose I have an algebraic group action of this H on some other variety Z. Then this action induces the natural diagonal action of H on a product G cross Z, which sends a pair. So a pair G comma Z, G comma small z, is mapped by an element of H to the pair GH inverse, comma H applied to Z. So the diagonal action of H on the product given by the actions on each factor. Now, let me formulate the following statement, theorem. If G is quasi-projective, if this variety Z is quasi-projective, then this action in the middle, the action of H on G cross Z, admits a geometric quotient. So there exists a geometric quotient for this action. There exists a geometric quotient for this action, which I shall denote as follows: G cross Z over H. This is the notation for this geometric quotient. And also, I will denote the point in this geometric quotient corresponding to the pair small g, small z in the following way. I will write G star Z. This is the point in the geometric quotient, the image of the pair G comma Z when you take the quotient by H. So this geometric quotient exists. This is the statement. This geometric quotient exists and has the following properties. Let me list the properties.
Is this a tensor product? Like,
it is not a tensor product. It is, sometimes it is called a product over a group, but I don't know any standard name. It is what is written here. It is by definition the geometric quotient of this product variety by the diagonal action of H, of a subgroup H. But let me discuss the properties of this new variety, and maybe you will understand understand more about the geometric meaning of this construction. So the first property is that there is a natural morphism. There is a natural map. Say again, let me denote it again by pi. It is not the pi which I used before, but so there is a natural map from this geometric quotient to the homogeneous variety which I previously denoted by y. It is the quotient of G modulo H. It sends, this map pi sends this point just to the coset of G in this quotient space, in this coset space. And this map is a morphism. Okay, this is the first property. The second property is that there is a natural action of G on this quotient variety given by this natural formula. So an element G acts on a point G prime star Z, giving the resulting point G star G prime star Z. So this action of G on the quotient is induced by the action of G on the product variety, G cross Z, on this variety by multiplication on the first factor. And this G action by multiplication on the first factor of this guy descends to the geometric quotient. So this is the second property. And the third property, let me formulate it as follows. Let me choose the base point on the quotient variety y, which is G over H. Let me denote it by x as before. So x is just the coset of the unity. Then the fiber of pi over this x, it is in the previous notation just E star the whole Z, is isomorphic to Z as an algebraic variety. And the fiber over any other point, say over the point y, which is the coset of G, in the previous notation it is G star big Z, is obtained from the fiber over X by the action of the element G. And therefore, it is also isomorphic to Z. So what is the picture? Let me draw a picture. The picture we have is the following. We have a variety Y, which is a homogeneous space. And we have a map from this quotient, this variety G cross HZ to Y, this map pi. Let me denote this map by this arrow. And we have fibers of this map pi over each point of Y. So over each point, we have a fiber. The fiber over the base point, X, is canonically identified with Z. And the fiber over any other point, say Y, which is obtained from X by an action of some group element, this fiber, so it is this guy, is also isomorphic to Z, and it is obtained from this fiber by the action of the same element. But now it acts it acts on the space above, on this geometric quotient space. So to summarize, we can say that this variety G cross over H Z cross Z over H is a fibration over the base Y, whose fibers with typical fiber Z and the other fibers are obtained from the typical fiber from the given fiber just by the group action. So the fibers are transitively permuted by G. Such kind of thing is usually called a homogeneous fiber bundle. Let me write the name. So homogeneous fiber bundle. So this guy is homogeneous, is a homogeneous fiber bundle. It is a fiber bundle over a homogeneous base. So Y is a homogeneous variety. G acts on Y transitively. And the fibers, and this G action lifts to the total space of the bundle. And the fibers of this bundle, of this fibration, are permuted transitively accordingly to the permutation of points on the base by the group action. So this is the picture you should keep in mind. And there is an important addition to this statement. So conversely, let me write it down here. Conversely, given any algebraic variety X equipped with an action of G, and such that there is a map pi, I again denoted by pi, from X to Y to a homogeneous space Y, to a homogeneous variety Y, which commutes with the action of G. So G acts on X, G acts on Y, and pi is equivariant, commuting with the G action. Equivariant. Then, if we denote by Z the fiber of this pi over a given point of Y, so over this base point X, if we denote this fiber by Z, or if it is isomorphic to Z, maybe it is more safe to say that let the fiber over X be isomorphic to Z. then the variety X is isomorphic with the fiber bundle, with the homogeneous fiber bundle G cross Z over H. And this isomorphism again commutes with the action of G. So essentially, a homogeneous fiber bundle is uniquely defined by its base and its typical fiber. This is how to summarize this last statement. Actually, this theorem is less standard, as I said. This theorem. Yes. Any question? Please.
Yes. Well.
Yeah. Please. Go ahead.
If we are given the condition that the projection pi is equivariant, could we conclude that the fiber Z is certainly or not? It must be a variety.
So the connection is weak, and I'm not sure I heard well your question. So if this pi is equivariant, then can we conclude what?
Can we
say
conclude
it again, please?
Z is a variety.
That Z is. I don't hear you well.
Can we conclude?
I'm sorry.
Z is a variety.
Yes, of course. Well, if you have a morphism of two algebraic varieties, then the fiber over any point is again an algebraic variety. It is a closed subvariety in X. This is very general for any morphism of algebraic varieties. Was it your question?
Yes. Thanks.
Okay. Good. So since this theorem is less standard, yes.
Okay,
yes,
so
please.
Do we assume Y is a priori a geometric quotient of some H, or we mean that we can find
yes, exactly.
Oh, okay.
Yes. Y is the same as before, the same as above. I keep the previous notation here.
Okay,
yeah.
Thank you.
Okay. So since this theorem is less standard, and I am not going to prove it, let me give a link. You can find a proof in an expository paper of Andrzej Balniski-Birula, for instance. Not only there, but for instance, in this paper. If you want to see the proof. So this was published in 1993 in Annals of the Fourier Institute in Grenoble. So this is volume 43 of 1993. Number 2, pages 365 till 368. Here you can see the proof of this fact. The title, well, I don't write the title, on induced actions of algebraic groups, because these coordinates are enough to find the paper. So if you look at Math.Scinet, for instance, or Centralblatt, and insert this data, then it is a unique paper with this data. On induced actions of algebraic groups, as far as I remember. This is the title. Okay. So in particular, let me switch to the next page. In particular, if you start with a linear representation of H in some vector space V, linear representation, then you may construct the homogeneous fiber bundle as above. G cross V over H, which is now a vector bundle. because the fiber is a vector space. Each fiber is a vector space. And it is called a homogeneous vector bundle. Over the same homogeneous variety, Y. Maybe I should try to copy this picture on the next slide. Let me try. Excuse me, no, this is the wrong way to do it. I think that I should do like this. Oops. Okay. So what I did? Yeah, something. Well, okay, let me do like this. Does it work? Sorry, I'm trying to play with this whiteboard. I see that I'm not quite skilled. No, it doesn't work like this. Well, maybe I should just rewrite what is written here. On the next page, it is quicker to do like this. Okay. I erase this. Yes. I'll put it here. So let me restore what was written there. So given a linear representation of H in a vector space V, we construct a homogeneous vector bundle okay. Okay, so now let me put small corrections here. This is not so easy. I'm sorry. So now Z is V. Z is a vector space. Here you also have a vector space. This is the total space E of my vector bundle, and the rest of the picture is the same. I'm sorry, I have to train more with this whiteboard. So far I see I'm not skilled enough. Okay. Once we have a vector bundle, we have a space of sections for this vector bundle. So we may consider sections. Of the vector bundle E over Y. And this space of sections is, of course, equipped with the natural action of G. G acts everywhere. G acts on Y, G acts on E. Fiber was linearly, and therefore it acts in the space of global sections of E over Y. And this action is a linear representation. It is called the induced representation. Induced representation.
GX on the section.
Yes, sure. Because GX on the base, GX on the total space, these two actions compute with the projection pi. So GX also on sections. you just can move the section, all values of the section along the action of any given element small g. And this representation space of the induced representation is also denoted in the following way. So this space is the space of the representation induced from H to G from the representation in the space V. So this is the notation for the space of the induced representation. This space can be described by the following lemma. The induced representation space is naturally isomorphic to the following. You take the algebra of regular functions on G, you tensor it with V, and you take invariance with respect to the diagonal action of H. So here H acts on V in the natural way, and the action of H on the polynomials on G comes from the action of H on G itself by right multiplication. More precisely, if you have a polynomial on G, a regular function of G, and you act on this function by some H, then the resulting function, its value at G is f of G times H. So this is how H acts on functions on G. Okay, so the proof is actually not difficult proof. What can you do? So we have this vector bundle E. Yeah.
Hey, Professor.
Yes. Yes.
We will not use group algebra in this course, right?
What do you mean by the group algebra?
Because KG will be confused with the group algebra KG.
Well, I mean, in the theory of finite groups, you sometimes use this notation. But in my algebraic geometric setting, this notation is just the what is called the coordinate algebra of the affine variety G. So it is the algebra of all regular functions on G as an affine variety. And I use this notation in the more general setting for any affine variety. I denote it by K of X in brackets, the algebra of regular functions on G.
Yes, I know that.
So I'm sorry if it is.
I'm
sorry if it is confusing.
Sure that we won't use group algebra to confuse.
No group algebra. No group algebra. No group algebra. Group algebra is a good thing for finite groups, but here the group is infinite. It is a Lie group, so there is no such a good notion of a group algebra in this case. There exist some versions, but we do not use it here. It is the algebra of regular functions, nothing more. Okay? So, coming back to the proof of the lemma. I see I have just a few minutes, 6 minutes, so I have to hurry up a little bit. So coming back to the proof of this lemma. So what can you do? You have this vector bundle, this homogeneous vector bundle over Y, and you can pull it back along the natural map from G to Y. This is just the orbit map. This map sends G small to the point G applied to X. So this point was also denoted by Y on the previous slide. This is the orbit map. And you can pull back this vector bundle along this orbit map. Let me denote this orbit map by phi. So you have the following Cartesian square. here this is the fiber product, so that this diagram is Cartesian. And less formally, you just pull back this vector bundle onto G over G along this map. This means that the fiber of this second bundle over G, over small g, is the same as the fiber of this first bundle over the image of G, over the point Y. So this is a pulled back vector bundle. And this pulled back vector bundle is already trivial. It is isomorphic to the direct product. Because for this second vector bundle, you can identify all fibers in a canonical way. You may take the fiber over unity, and all other fibers are obtained from the fiber over unity by the action of a unique element of the group. Because the group G acts on itself simply transitively. The stabilizer is trivial. So this pulled back vector bundle trivializes. And now what can you do? So suppose you have a section. Suppose you have some section S. You can lift this section here. Pull back this section to get the section of this vector bundle. And this is a section of the trivial vector bundle. So it is given just by a map from G to the typical fiber. Let me denote this map by F. So the relation between these maps is the following one. So phi star S at the point G is the same as the pair S of the point G dot X and G. So this pair is a point in here, in this fiber product. And the value of the section S at this point sits actually in the fiber of this point. So it sits in the previous notation, it sits in here. But you want to get a vector in V itself. So you define this vector, f of G, just by applying the element G inverse to the value of the section S at the point Jx. So, and then you get from this fiber to the fiber over unity, so to V itself. So this is how this map from G to V is defined. And let me observe that this map commutes with the action of H. We have the following: f of G times H inverse equals to H applied to f of G. So the map F commutes with the action of H. And conversely,
what? I think we define.
Yeah.
Oh,
I'm not hearing you.
No, Hx on V. No, I
yeah, Hx on V. Hx on V. Yeah, yeah. So conversely.
I'm sorry, Professor.
Yes.
So what?
Yes, please.
So I'm a little lost for the x here. The little x.
What is x? Yeah, actually x is the base point in here. So if you identify your y with the coset space, then x is the coset of unity. Okay. So recall that y is identified with the coset space G over H. So this X is some fixed point in Y, the base point. Okay?
It must be EH, right? Or we can just
Yes, yes, it is EH.
Okay.
The point, the fixed base point with stabilizer H. So this map F is H invariant. It commutes with the action of H on both G and V. And conversely, every such a map, so if you have an H invariant map from G to V, and such a map is an element of this tensor product. Okay? Because F is a vector function. So a vector function is for each coordinate you get, for each coordinate on V, you get just a scalar valued function, a regular function on G. And a vector function sits in the space which is here in parentheses. And if you have an H invariant vector function, then such a function can descend to a section of my vector bundle E, descends to a section. Descends to a section. Which is given if you revert the above formula. So the value of the section at the point G applied to X is G star F of G. What I have done, I just took this formula, this one, and acted by G on the left side and on the right side. So on the right side, I got the value of section S here, and on the left side, I got this this guy. So this is how to restore the section from the map F, and for any map F, you can get such a section. So this gives you a one-to-one correspondence and isomorphism between these two vector spaces. I think I should stop here because I'm already 3 minutes out of time. So thank you for your attention. Thank you. If you have any questions, then again, you are free. Feel free to ask.
So again, the H0 YE is just the in GHV, this vector space, right? Because I don't see why you write this representation over there.
So this space is the space of global section of this vector bundle over the base Y, which is a homogeneous variety. And this is just the notation. This space is denoted like this. And it is called the induced representation of G. The induced representation space. The space of the induced representation, yeah? So this is how induction of representations can be defined in the setting of algebraic groups. Was it your question?
Professor, so in the right, we have a vector space over Kg, right?
No, we have vector space over K, not over Kg. Actually, of course, this vector space is a module over the algebra of regular functions over Y. But I consider it just as a vector space. It may be infinite dimensional, by the way. So in general, this is an infinite dimensional representation. But for instance, if your Y is compact, maybe it's better to say complete variety, then standard theorems of algebraic geometry tell you that this space of sections is finite dimensional. So in some interesting cases, it is finite dimensional, but generally infinite dimensional. Okay.
Well, so I'm not very clear about the definition of lemma in the right. So what is?
So what is written here in the right? Yeah. What is written here in the right? So this is again general notation. When you write the group as the upper subscript, as the superscript, or on above, then this means that you consider H invariant elements, H invariant points, points which are fixed by the action of H. And what does it mean here? H acts on this tensor product because it acts on each factor, on each tensor factor. The action of H on V is given by this linear representation, and the action of H on the algebra of functions on G is given by this formula. It comes from the action of H on the group G itself by right translations.
And should it be H minus 1 here? I mean,
here not, because when you act on an argument of a function, you have to act by an inverse element of the group. And when you act by right translation, you already multiply by inverse. So here you should multiply by H inverse inverse. This means by H itself. This is just quite formal from the definition of the group action. If a group acts on some set, then it acts on functions on this set. And when you act on a function, you have to apply G inverse to an argument of a function. And since the action of H by right translation already includes inverses, then you take inverse twice, and this means that you multiply just by H itself, like this. Any other questions or comments?
Is it a linear representation here? H action on the KG.
Yes, of course, it is a linear representation. When a group acts on a set, you get a linear representation in the space of functions on this set. This is quite general.
So we just consider the bilinear representation here, and we consider those elements that are fixed by H.
Exactly.
Okay.
More questions? Comments? Well, maybe then we can stop the lecture now, but I have a small addendum because I was asked by Huhaim, and this was a question, as I guess this was a question from the students, from some of you. What is the form of homeworks, and what is the percentage of homeworks and exams in the final grade? Am I right that you asked such a question?
Yes, I asked such a question.
Yeah, okay. So let's agree with the following. As for homework, then I give you exercises. During the lectures, I give you exercises. You have already seen some of the exercises, and you can send me the solutions to the exercises by email. You have my email, so you can send the solutions on email, on this email. As for a relation between homework and exam, its percentage to the final grade. Actually, I'm not quite skilled in Chinese system. I don't know what you are used to, but maybe if we put, so final grade is for 100%, and if we put 50% here and 50% here, will it be okay? Any objections?
Yes. What's your email?
Yeah. Okay, so let's agree that the final grade will be 50% by results of your homeworks and 50% by results of the final exam. As for homeworks, please send me the solutions to exercises on email. Okay?
Yes, what's your email?
What is my email? If you open the notes of the first lecture, and it is available, I guess the link is in the web chat, in the chat, there should be a link. Let me check. At least it was there. Yeah. So there is a link to the recordings, and also the notes are put there to the same place. So if you open the notes of my first lecture and go to the last page, you will get my email. Okay? So just use the link in the chat at the beginning of the web chat. A link from Huchaim. Okay, so more questions? If not, thank you again for your attention.
Can we ask questions?
Yeah. Yes, sure. Please.
Can we ask questions through your email?
Yes. Feel free to write me. Sure. So if there are no more questions, then we can finish today's lecture. And I hope to see you all on Monday, next Monday.
Okay, thank you for the lecture.
Thank you, Huchaim, for your assistance. Thank you. So you will put the recording at the same place, yeah?
Yeah, and I will resend them the link.
Great.
Yeah.
That would be nice. Please resend the link to the students. So everything will be there.
Yeah.
Okay, so then I'm stopping. I stop sharing and bye-bye. See you on Monday.
Bye-bye.